Welcome back to the final lecture of this shortened week. In this lecture, we will talk about the intermediate value theorem. This lecture is a bit longer compared to the other two since the intermediate value theorem has some nice applications that I want to mention. This lecture corresponds to pages 134 through 136 of your textbook. Before discussing the intermediate value theorem, let's first discuss the intermediate value property. A function f is said to have the intermediate value property if, for every a less than b, both in the domain of f, and for every gamma between f of a and f of b, there exists some c between a and b such that f of c equals gamma. Notice that if f of a equals f of b, then gamma being between them will mean that gamma is equal to both f of a and f of b. And setting c equals a or c equals b will solve the problem. So we are primarily interested when f of a and f of b are not equal. The phrasing with gamma between f of a and f of b allows either f of a to be larger or f of b to be larger. It is perhaps easiest to understand the statement of the property by a picture. Here we plot an axis and 2 points a and b within the domain of f. We'll go through how one may check that a function has the intermediate value property or not. This f may have f of a larger than f of b. Here I just show its values near a and b, and leave the rest inside as a mystery. To test whether f satisfies the intermediate value property, we take some gamma between f of a and f of b. Notice that this is represented by a horizontal line on the graph. It is a given level that we are seeking. It turns out our function does have a solution to f of c equals gamma. Let's mark it on the graph. To be able to find c between a and b that solves f of c equals gamma means that the graph of f must intersect this horizontal line somewhere. So I show a bit of the graph also. Since the statement of the property requires the solvability to hold for all gamma, let's do the same thing with another gamma prime. Again, this is represented by a horizontal line. It turns out this time, the line gamma prime hits the graph of f 3 times, at 3 different points. We mark them C prime 1, C prime 2, and C prime 3. A bit of the function is also shown. Now let's review the underlying function. The yellow curve here is the value of f over the interval ab. Notice that f is not continuous, at least not how I drew it. But between a and b, the condition for the intermediate value property seems to be met. Indeed, if you try to draw a horizontal line corresponding to any value between f of a and f of b, you will find that the horizontal line intersects the yellow curve somewhere, and this intersection corresponds to a value on the x-axis that is between a and b. But the statement of the intermediate value property is not only a for all gamma, it also has a for all a and b. So let's move a around a little bit. We can move a to the value a prime shown on the picture here. Notice that we get a new value of f of a prime. To test the intermediate value property using a prime and b, we have to pick a value gamma between f of a prime and f of b. Say, this one. Now, while this horizontal line does in fact intersect the yellow curve, it does so at an x value that is less than a prime. That is, outside the interval a prime to b. There is in fact no intersection of the gamma horizontal line with the function f within the interval a prime to b. And this last test shows us that our function does not, in fact, satisfy the intermediate value property. So, the take-home message, there are many quantifiers in the statement of the intermediate value property. There are infinitely many combinations of endpoints to make different intervals, and there are infinitely many intermediate gamma to choose. So having intermediate value property is not something that can be said for most functions. Having explained the intermediate value property, we can state the intermediate value theorem. It simply says that every continuous function defined on an interval I has the intermediate value property. I should note at this point that the fact that a continuous function is defined on an interval I does not mean you should only check the intermediate value property using the endpoints of I for reference. The intermediate value property is holding for any subinterval of I. Before giving the key step of the proof, let's do some preliminary work. Since the f has domain and interval, we can slightly simplify the intermediate value property to saying that if the closed interval AB is a subinterval of I, and gamma is a point between f of A and f of B, then there is a C in the interval AB such that f of C equals gamma. This statement is largely the same as what we gave before, but with some minor simplifications due to what the domain of f is. On your exercise sheet, you will be asked to think about this a bit more. Now, there are three cases we need to treat. First, it may be that f of A equals f of B. In this case, we can just choose C to be A and B and be done with it. So we're down to the more interesting cases where f of A is either larger or smaller than f of B. In the video, we will prove the latter case. The other case has very similar proof. Before writing down the proof in words, it may help to watch it go by in cartoon form. On this graph, we plotted a function that is continuous and an interval AB. This is one of the many subintervals we must contend with to prove that f has the intermediate value property. The corresponding values of f of A and f of B are marked. We see that f of A is less than f of B. Suppose we wish to find a solution to f of C equals gamma, where gamma is the purple line drawn here. Notice that from our bird's eye view, we see that there are 5 different solutions to this problem. We just need to find an algorithm that guarantees that we find one of the 5 points. How do we do it? What we will do is to look at a portion of the function that sits below the line y equals gamma. Here, I color it in light blue. The corresponding x values, which leads to the function being below gamma, we collect into a set called capital A. On the x-axis, I colored in the set A. In this picture, it has 3 segments. Notice that since f of A is less than gamma, it takes the place of the endpoint of the leftmost segment. The 5 remaining endpoints actually correspond to the 5 solutions of our problem. And notice that f of B, being strictly bigger than gamma, sits some ways away from the rightmost segment. Notice that we only really care about the cases where gamma is strictly between f of A and f of B. If gamma is equal to either f of A or f of B, then we can just set C to be A or B respectively and be done with the proof. Before going further, I wish to remark that while I use a set of values that lie below the line gamma, you can also equally well use a set of values that lie above the line for this construction if you make some appropriate changes. Anyway, back to the proof. The idea is that we will pick out one special endpoint. We will pick the endpoint that is the largest value among the set A. The choice of largest value is so that it allows us to make use of all the tools about supremum that we learned and developed in this course so far. You may wonder why we don't use the smallest point and the infimum. In this case, this is because, as we already observed, the smallest element of the set capital A is going to be the point small a, which is unfortunately not a solution to our problem. So what's so great about the supremum? The supremum of A is a solution because if we just go a little bit north of it, we enter into the territory where f of x is greater than gamma. And if we go just a little bit south of it, we enter into the set A. So we expect the sup of A is exactly the dividing line, which will mean that f of the sup of A is exactly gamma. Now let's try to make this precise. First, some setup. Just writing down what we showed in the cartoon in words. We let A be the set of all x values such that f of x is less than or equal to gamma. As we noted earlier, A is an element, B is not. We take C to be sup of A. This C is definitely an element of the interval AB. This is because A is an element of A and C is larger than A, being an upper bound. And since the set A is a subset of the interval AB, we know that B is an upper bound of the set, and hence is greater than the least upper bound C. So at this point, we have given an algorithm that, given an arbitrary subinterval AB and a value gamma between f of A and f of B, picks out a point C that lies inside the interval AB. So all we need to do is to prove that f of C is equal to gamma. To do so, we will use the classic argument and prove that f of C is both at least and no more than gamma. We prove first that f of C is no more than gamma. Since A is a bounded set, we can take Xn a maximizing sequence of A. If you don't remember what a maximizing sequence is, please go back and rewatch Lecture 2 video. By definition, this maximizing sequence converges to C. Since every xn is an element of A, we know that f of xn is no more than gamma. This means that the limit of the sequence f of xn is also no more than gamma from the comparison theorem. But since f is continuous, we know that f of c is equal to the limit of f of xn. So f of c is also no more than gamma. To summarize, since C is the supremum of the set A, we can approach C from below inside the set A. And since f of x for x in A is less than or equal to gamma, continuity guarantees that f of C is no more than gamma. Next, we prove that f of C is at least gamma. By the previous step, we already know that f of c is no more than gamma, so in particular, since f of b is greater than gamma, we know that b is not c. So this means we can build a sequence inside the interval from c to b that converges to c from above. To be concrete, I give an explicit construction on this slide. Choose first some large n such that c plus 1 over n is between c and b. Then just take the sequence y sub n to be c plus 1 over capital N plus small n. This sequence converges to C, and since every element of this sequence is larger than C, they cannot be elements of A, and hence f of yn are all greater than gamma. The comparison theorem and continuity again then tells us that f of c, being the limit of f of yn, has to be at least gamma. Notice here that even though term by term f of yn are strictly bigger than gamma, the best we can say about the limit is that f of c is bigger than or equal to gamma. You have already encountered this caveat last week. In any case, this concludes our proof. As you can see, the main work that was done is making precise mathematically the idea that if you go a bit beyond sup of A, you enter the realm of f bigger than gamma, and if you go a bit shy of sup of A, you get points whose f values is less than gamma. And then to take advantage of it to show that f of sup of A has to be equal to gamma. Next, we discuss some applications of the intermediate value theorem. The first is a corollary obtained by combining the intermediate and extremal value theorems. It says that if f is a continuous function defined on a closed interval ab, then the range of f is also a closed interval. The proof is only 2 lines. By the extremal value theorem, there is a finite global maximum value and a finite global minimum value. These correspond to 2 points C and D in the domain. Over the subinterval bounded by C and D, the function f is a continuous function, and hence every value between f of C and f of D can be realized by some z between C and D. And together, this shows that every number between f of C and f of D appears as an output of f, and every output of f is between f of C and f of D, and hence the interval is the set of all outputs. Let's compare the intermediate value theorem to the extremal value theorem. Whereas the extremal value theorem is useful for solving optimization problems, the intermediate value problem is useful for solving interpolation problems. Besides the fact that, based on the previous corollary, f is a surjection onto the interval between its minimum and maximum values, here is another application to demonstrate how the intermediate value theorem may be used. This is a theorem. If f is a continuous function with domain AB and takes value in the same interval, then there is a point C on the interval for which f of C equals C. This is what is called a fixed point theorem, and is useful for finding out whether there is stationary behavior hidden within an otherwise dynamical process. Here is the proof. We build an auxiliary function g of x being f of x minus x. Since the range of f is inside the interval ab, we know that f of a has to be at least a, and f of b is no more than b. Translated to the function g, this means that g of a is non-negative, and g of b is non-positive. And thus, 0 is guaranteed as a value between g of a and g of b. So, by the intermediate value theorem, for some c in the domain, we have g of c is 0. Unwrapping this, we find exactly that f of c is equal to c. The final theorem of this week is a partial converse of the intermediate value theorem. The intermediate value theorem states that the continuous functions have the intermediate value property. Is the converse true? Is it the case that functions that have the intermediate value property must be continuous? In the 19th century, for a while, it was believed that the intermediate value property is what characterizes continuous functions, and attempts were made to develop calculus based on it. These all ultimately failed, as it turns out that this is not the case. On your homework, you will be exploring some counterexamples. However, it turns out that intermediate value property is very close to continuity. It just needs a little tiny kick, and over the hump it goes. There are many different ways of applying this kick. One of them is this theorem here. If we take the intermediate value property for a function defined on an interval, and add to it the condition that a function is increasing, then, in fact, f has to be continuous. The basic idea behind this theorem is that if a function is increasing, then the only way it can be discontinuous is by having jump discontinuities. But on the other hand, jump discontinuities are expressly forbidden by the intermediate value property. I hope you spend a few minutes convincing yourself of both facts. So this is the proof strategy. Let z in I and epsilon positive be arbitrary. To show that f is continuous, we need to show we can find a delta such that if x is within delta of z, then f of x is within epsilon of f of z. We will split up our construction in half, treating the half below z and the half above z separately. For each half, we will construct a corresponding delta minus and delta plus to make the conclusion satisfied. And then we will combine the two cases by choosing delta to be the lesser of delta minus and delta plus. The fact that we can split up our construction in half is due to the function f being increasing. No inputs less than z will give an output greater than f of z and vice versa. And so the two halves can be treated separately. We will focus our effort then in finding some delta minus such that if x is less than z but by no more than delta minus, then f of x is within epsilon of f of z. There are two cases. First, it is possible that we don't need to do any work. It may be the case that for all elements in the domain of f that are less than z, we have that their corresponding outputs are never more than epsilon away from f of z. In this case, we can choose any random delta minus and it will satisfy our needs. If we are not so lucky, then there is some x minus that is smaller than z, and such that f of x minus is less than f of z minus epsilon. But using the intermediate value property, this means we can find some delta minus such that f of z minus delta minus has value f of z minus 1/2 epsilon. Using that f is increasing, this means that any input between z minus delta minus and z will result in an output between f of z minus 1/2 epsilon and f of z, exactly as we needed. And doing the same thing for the other side, we can construct a delta plus using the strategy from the previous slide. This proves the theorem. All right, that's it for this week. Next week, we will move on and talk about derivatives. See ya!